Are you obsessed with Jennifer Aniston? I mean, who isn't? But I mean, really obsessed. Like break into her house, get caught, and take off your shirt in court obsessed. Okay, maybe not that obsessed. But like Ross, you want to be more than friends, and she's literally all you can think about. In 2005, scientists recorded the neurons of a patient undergoing treatment for epilepsy, and there they found a neuron that only fired for Jennifer Aniston. Not for David Schwimmer, not for Courtney Cox, just Jennifer Aniston. This idea isn't the plot of a sitcom. It's actually a famous hypothesis in neuroscience. The grandmother neuron hypothesis. The idea is that somewhere in your brain, a single neuron is responsible for representing your grandmother, or in this case, Jennifer Aniston. But is that how brains really work? Not quite. Studies have shown that our brains represent people, objects, and other concepts through clusters of neurons. Picture it like a Venn diagram. Both a cat and a human light up the face cluster, but only humans also trigger the person cluster. This distribution of concepts also makes the system robust. If a single neuron dies, the idea stays intact. But the Jennifer Aniston neuron just sounds nice and clickbaity. And in the world of science, attention is all you need. Okay, so we know brains don't really work that way. But what about artificial brains? Brains and neural networks are built differently, so maybe they work more like the grandmother neuron idea. I trained a small ResNet network to recognize, or in machine learning terms, classify, the cast of Friends. Could there be a single neuron responsible for recognizing Rachel? A Ross neuron, if you will? Let's test it by zeroing out the weights of the network one at a time, and checking whether disabling that weight breaks the classifier. Well, it didn't break the classifier. It turns out that just like in the brain, that there's no single weight that represents Jennifer Aniston. Multiple weights are responsible for recognizing her. Just like real brains, neural networks are somewhat robust against small damage. I think we should abandon the idea of a single neuron changing the classification. I think we should... What if, instead of one neuron, there's a whole bunch of them, like a little fan club, and taking them out breaks the classifier? Our new goal is to find the smallest set of weights whose removal causes the network to fail. With 0% of the weights zeroed out, the classifier obviously works just fine. With 100% of the weights disabled, it completely fails. So somewhere in between lies the tipping point. We could test every possible size one by one, but that would take forever. So instead, we use bisectioning, or binary search. The idea is that we try 50%, and if the classifier fails, the critical point must fall below that. Then we try 25%, and if it still works, we go back up. Each step narrows the range until we find the smallest set of weights. Let's try this. With just 53.9% of the weights disabled, the classifier changes its decision to Chandler. But because the weights chosen to be removed are random, we need to repeat this process a few times. After repeating the experiment 10 times, the smallest set that changes the classification is just 500,000 weights. In this example, I changed the weights of the network. But in many real-life cases, you don't have access to the network weights. So what if we change the pixels of the image instead? What is the fewest number of pixels we need to change to flip the classification? Can you spot the difference between these two images? We call this rather pleonastic term an adversarial attack. You can use it in real life to trick self-driving cars into thinking that a stop sign is Jennifer Aniston by putting stickers on them. In conclusion, no single neuron is responsible for recognizing Jennifer Aniston, not in the brain and not in artificial neural networks. Because, as it turns out, recognition isn't a solo act. For it to work, you need friends.